Good morning, good evening, wherever and whenever you may be. I'm SpiderDevice, and welcome to Web Talks. This is episode 7, putting it all together in consolidation. In this episode, we'll be doing just that, looking at how to put together all of the components we've covered until now, and how they all interface with each other. We'll look at consolidation. How do we make the web shooter as small and compact as possible, while still retaining functionality? What trade-offs do we have to make in order to maximize our functionality, while keeping our ease of use at an acceptable level? And on that note, we'll make certain remarks about designing with regards to functionality, and bring to light some concerns you may not have thought of before regarding operation of the web shooter. Before we begin, I'd like to just note that this is the final planned episode of Web Talks. Thank you all for watching the videos, using them as a resource, and using them to drive your interest in the project. As little content as I can release these days, please know the support is highly appreciated. We'll discuss the future of Web Talks at a later date. Now let's get into this episode. First, let's get a sense of how all the components we've covered in the series interface with each other, and how the flow of the input, the trigger, will relate to the flow of the output, the web shooting. The formula itself, which we covered in episodes 2 and 3, is stored within one or more pressure vessels, high-pressure capable canisters where the fluid is stored, along with some propellant, until it's released. You can learn more about the pressure vessel itself in episode 4. The component that controls the release of this fluid is known as the release valve, which in and of itself can be triggered by some kind of actuator, in which case the actuator would be acted on by the trigger. See episode 5 for further explanation on this. Either way, the way this release valve is opened is via some kind of trigger, which in itself can have some kind of control mechanism in the form of digital logic or force conversion in more direct cases. Information on this is also in episode 5. From the release valve, fluid travels through some kind of tubing, and once consolidated is extruded with high pressure through the spinneret or directing mechanism, both of which I explained in episode 1. Now this is the essential construction of this type of web shooter. We're not really taking into account the so-called web shooters that have no fluid and only shoot some kind of projectile connected to a cable. While that may be perfectly legitimate as far as sheer invention goes, I don't personally consider it to be a web shooter, as it's more of just a grapple device. With all of these parts, it's kind of hard to know which parts are able to be eliminated or consolidated. First, let's establish which components are common, or at least comparable, throughout all web shooter builds. These would be the spinneret/directing mechanism, the tubing, the pressure vessel, and the fluid itself. All of these components will take various forms throughout each build, but each retains essentially the same functionality within the shooter itself, no matter the build. Let's first talk about the fluid and its connection to the pressure vessel, as it's going to be the driving factor behind how we build the web shooter on the whole. First, we have to look at what kind of chemical process or reaction is taking place to change the fluid from, just that, a fluid, into the solid web. In most cases, this will just be the simple evaporation of a solvent such as acetone. In other cases, shearing properties, aeration, or the mixing of chemicals will cause the fluid to harden. As such, we need to establish how the fluid is going to be stored and in what quantities. It's at this point we have to think about the balance between portability and usability. In essence, as the amount of fluid you carry goes up, portability and concealability will go down. Something I don't see a lot of people taking into account is how much yield will actually be obtained from the amount of fluid, or the size of pressure vessel, that they're carrying. What do I mean by yield? Well, when you think about it, you have to take into account that we are shearing this formula through a spinneret, which, given the small size of the ideal strands, will change the perceived amount of web that we're creating. This is to say that if we're trying to make a web line, the length of the line we can create will depend not only on the amount of fluid, but on the size of the hole or holes in the spinneret. Now this may seem obvious to some of you, but it's a good gauge to use the size of the extrusion ports on the shooter to find out how long of a line you're going to be able to produce overall. Thus, we can change the volume we're carrying based on the total length of web that we want to carry, rather than focusing on the sheer amount of fluid. We can also vary the size of the extrusion ports on the spinneret and do some volume conversion math to figure out the new length. However, this is only one aspect of figuring out how much fluid you want to carry. In most cases, there will be a change in the overall volume when the fluid is a liquid as opposed to when it's in the solid state. When you take into account solvent evaporation, aeration, shearing properties, and to a small extent the self-siphoning property, which I'll talk about later, you'll find that the volume of fluid you're carrying won't directly correlate to the volume of webbing you'll produce due to these factors. As such, in addition to using the aforementioned method to estimate the length of web line you'll produce, you should, ideally, make a certain amount of formula, extrude it, and do a water displacement test in order to find the total volume of your yield versus what's actually been taken out of the pressure vessel. Let's lead into talking about exclusively the pressure vessel by finally addressing something I've seen mentioned but I've never really addressed, and I think it really needs to be said. Actually, I have addressed it before. In fact, I made a pretty significant point of it in Small Talks episode 3. Therefore, a badness was committed. Carry on. A lot of people have asked why we can't just take the fluid itself and compress it. The fact is, that's just not possible on a fundamental level. Liquid as a state of matter cannot be compressed. The molecules are simply too close together as it is. Any compression that would happen, assuming you'd be able to mount the absolutely enormous amount of pressure to do it, would be insanely minimal. So the idea of compressing a liquid is out of the question. That said, we do have to think about compression of gas and pressure. Now, maximum pressure that your pressure vessel can hold is going to vary depending on the material from which it's made, and you'll have to look up the specifications yourself for whatever material you're considering. Spider-Man's fluid in the comics is said to be at about 300 psi, but given the shape of his canisters and the expansion effect that I described in the pressure vessel episode, we should really look to real applications to find a true threshold. For example, the maximum operating pressure for Schedule 40 3/4 inch PVC pipe is about 289 psi, and that's the material I use for my pressure vessels. A CO2 canister like the ones I've shown on my channel has a pressure of about 850 psi when sealed. Now obviously the gas is compressed into such a small space that connecting it to the pressure vessel will cause the pressure to drop dramatically, and I even did a test to be sure that these two would work together. But the point I'm trying to make is that you shouldn't need this high of pressure to propel the web. In fact, it may be detrimental to go this high, as it could damage your release valve and spinneret, as well as prematurely aerate your formula and damage its integrity. In general, about 115 psi should do, and depending on the size of the pressure vessel you're using and what other materials will be interacting with the pressurized formula, you could really go anywhere from 90 to 130 psi. However, going above, I'd say about 150 psi may be pushing it, especially considering the weakness of common materials I've seen pressure vessels made of. However, this is once again going to be up to your own testing and the material that your pressure vessel is made of. The most common way to apply pressure into a pressure vessel is to have an opening on one end leading to the release valve, and having the other end connected to some kind of compressed gas form, whether that simply be applying compressed air beforehand, or constantly having a CO2 canister connected. Having something like a CO2 canister does give you more consistent pressure, and will overall have the highest pressure applied most of the time. However, the drawback is that the CO2 canister itself will take up considerable space on the wrist. There are alternatives to this though. One of these would simply be putting compressed air into the canister via some kind of one-way valve. Then you could easily monitor air pressure with your air compressor that you're using, and you wouldn't have to worry about the extra space taken up by the CO2 canister. The drawback is that as the fluid escapes, its volume in the pressure vessel will decrease, and the gas volume will increase, thus making the pressure become lesser and lesser. The final way is something that The Amazing has been doing for quite some time, and that's actually putting a propellant into the same chamber as the formula. The propellant is put into the same chamber as the formula and often mixes with it. The formula is then kept at a low temperature, and when it's taken out, the propellant returns to a gaseous state as the temperature increases naturally, thus creating the pressure within the container. While this may not provide the most consistent pressure, it is the easiest way to provide pressure to the fluid. Personally, I think that having a CO2 canister is worth the sacrifice of space, considering it's not like you're going to have a giant tank on your back or anything, but it is up to you and what you're looking to achieve with the shooter. None of these methods, however, account for what happens if the fluid isn't directly in contact with some kind of internal straw, or isn't being constantly directly fed toward the release valve. Use of a piston between the pressure source and the fluid can alleviate this, and I'll direct you to the pressure vessel episode to learn more about this gas piston mechanism rather than completely explaining it again here. But suffice it to say that a piston isn't necessary, but it is useful. It is, however, not really compatible with the method of putting the propellant mixed in with the formula. Let's make a final note on the pressure vessel by talking about the tubing. In the pressure vessel episode of Web Talks, I defined the pressure vessel as a container that holds the web formula, or fluid as it were, under high pressure and has some mechanism that interfaces with the shooter, allowing the formula to exit the vessel on command of the shooter's user. Let's focus on the fact that the pressure vessel is the container under high pressure in which the fluid resides. If you think about it, while the release valve is open, any tubing that comes between the formal pressure vessel and the final extrusion point could still be considered part of the pressure vessel, as it's going to endure comparable pressure during extrusion. As such, you need to make sure that any tubing you use isn't just bare tubing. It needs to be reinforced somehow to be able to withstand the high pressure. Now, admittedly, the fluid is going to be moving at quite a high speed within this tubing most of the time, and it will be open to the outside through the eventual directing mechanism, so the pressure won't be nearly what it is inside the idle pressure vessel, but it will still be fairly high, all things considered. Even if you're using some kind of heating coil and have copper or some other metal tubing, there are instances where even that may be too thin and can burst. Make sure you reinforce any tubing you use just as well as you reinforce the pressure vessel itself. I also made a small talks episode where I detailed how fluid can get caught within this tubing, and how it can possibly dry or harden and cause clogging. I feel it should be mentioned again here, especially if you're going to go quite a while between each usage session of the shooter. Even if you're using something like a heating coil, or even if you're not, make sure that any tubing that's not part of the actual pressure vessel itself, part of the release valve or part of the directing mechanism, is as short as possible while still allowing the web to be formed as desired. Ideally, you'd want to eliminate tubing as much as possible so that you're as close to a configuration where each component in the fluid extrusion pipeline is directly connected to each other. This may require using extra resources for tubing and testing, and it may take quite a while to find the ideal amount of tubing, but it will save you a lot of hassle in the long run. The final element that I'll cover really in depth here is the spinneret, and this is the hardest element to talk about in this respect. Spinnerets and directing mechanisms can come in so many different sizes and are created to form so many different webbing types that consolidation is going to be difficult. The spinneret has to be created with the properties of the formula in mind. For a formula that utilizes aeration, a larger main extrusion port may be necessary, probably with a diameter between 1/4 inch and 1/2 inch. If you're using a formula where you mix the propellant in with the fluid, try decreasing the size of the extrusion ports. This way, the overall decreased amount of pressure you're creating can be maximized by increasing the velocity of your webbing by putting it through these smaller holes. 3D printing allows us to create spinnerets to really any specification or size we want, and we're even able to create new mechanisms therein. For example, we could even create a turbine, which will turn and actually spin a web just by the sheer pressure of the fluid being passed through it. Now, this wouldn't work with every formula, as you would have to have one that's not at all at risk of dissolving the material the spinneret's made from, and also isn't at risk of being too viscous or solidified while going through this turbine. In fact, it's said that Spider-Man himself uses a sort of turbine in the comics, so I think it's worth looking into, even if you end up having to create a turbine separately and routing the circular motion away towards a separate spinneret. Speaking of creating a spinning spinneret, one has to keep in mind that in order for a moving element to be within the fluid ejection pipeline, there has to be some sort of space to allow movement. I see people trying to say that they can simply mount a free-moving piece axially onto the end of the shooter. However, you have to keep in mind that it's likely that the amount of space required to allow the movement of this piece may be comparable to the small size of the ejection ports themselves. Thus, with the high pressure, the fluid may begin to shoot out of the area where the spinneret itself is connected. As such, the moving part or parts of such an apparatus should be contained within the fluid pipeline itself, and if that's not possible, then an effective seal must be created and maintained at all times so that the fluid will only be shot out of the proper ejection ports. I've already talked about clogging a little bit, and that may increase with what I'm about to talk about. But something I really want to cover here that's actually really interesting and useful when considering your fluid and appropriate spinneret is the self-siphoning property, which I said I would explain in this episode. Without getting too in-depth, basically the self-siphoning property is a property of a solution, where the molecules in solution actually have a slight interlocking effect with each other's outermost atoms, and as such the fluid becomes somewhat elastic and incredibly cohesive. Essentially, if you were to create a self-siphoning fluid or gel, if you tipped a cup full of it over and then lifted it back up so you weren't pouring it anymore, the fluid would still siphon itself out, pulling itself out almost like a coiled rope, because all of these molecules in solution are interlocked with each other. Similarly, if you were to put a spinning rod into a fluid with this property, the fluid itself would actually begin to climb up the rod. We can actually take advantage of the self-siphoning property and use it within the spinneret. As the spinneret spins, it can form the webbing into a cohesive line, and almost have a drawing effect like nylon. This is kind of a stretch, considering the spinneret itself also does have the job of catalyzing the solidification of the fluid, but since self-siphoning fluids and gels are often non-Newtonian, elastic, and easy to create, it could be an interesting application to look into. We still haven't really talked about the trigger or the release valve and actuator, and that's really because there's not much to say. The system by which your shooter functions fundamentally is going to determine the type of trigger and release valve you'll need, and in general, really the only way to consolidate these components is simply to create or purchase the same thing, but in a physically smaller size. For example, the best way to obtain a smaller solenoid valve is to literally just buy or build a smaller solenoid valve. For the most part, as the trigger and release valve are sort of intertwined, you'll need to change one if you fundamentally change the system by which the other operates. Once again, the most consolidation you can really do with these is really just decreasing the size of them. It's really all up to you. And that's the essence of this project. It's all up to you. As much as I can try to teach about the web shooter, its origins, its components, and the science behind it, the real ingenuity and the real spirit of invention comes from all of you. And that too has been the essence of this series. Not to dictate how you go about creating this incredible piece of technology, but to give you a stepping stone into creating your own real, amazing piece of superhero technology, and to give you knowledge that translates to countless other applications. And I feel that this series up to this point has done that, at least on some level. What's the future for Web Talks? We'll have to wait and see. But the future of real Spider-Man technology for now is up to you. Thank you all for supporting the channel and supporting this series time after time. Until next we meet, thank you all for watching. SpiderDevice out.